I think my question is it's a good introductory one, and it doesn't even just apply to just chemistry. It's good scientific thinking across different subjects, different subject material, physics, biology, and like even outside of science, just kind of statistics in general. I think my question is, how do you approach reading graphs and data in scientific work?
So let's go find a graph and from probably from Cengage, and let's see how I approach it. And let's see what comes up with that. So this is a graph with lots of incomprehensible numbers on it, right? I mean, what do we got? Okay, so but how am I approaching it? I don't really know what this graph is about. I think I'm probably supposed to know, but I don't. I'm gonna have to think about this a little bit because I haven't looked at this one for a little while. And I think the point of this one has to do with this straight line tells me something that's really important, but I don't know what it is. And so if I try to approach reading this graph, the first thing I'm gonna do is I'm gonna look at these. What's the label on these axes over here? Okay, so this one says it's the natural logarithm of the pressure, where pressure has units of millimeters of mercury. Okay, so there is some pressure value over here on this side. And underneath, it's oh man, it's the inverse of the temperature. What in the world is the inverse of the temperature? Okay, I have no idea what that's supposed to mean, right? Because it's the reciprocal of the temperature, right? And temperature is molecular motion, and the inverse of the temperature. Yeah, I have no idea what this graph is trying to tell me. But for some reason, they put it in here, and I think the straight line is really important, that it proves something important. And so I'm going to look up here and see if I can find some of the explanation for this. Okay. So the question was, determine the enthalpy of vaporization graphically using the Clausius-Clapeyron equation. Okay, I think vaporization is the amount of energy, or is the process of going from a liquid to a gas. The enthalpy of vaporization is going to be the amount of energy that it takes to go from a liquid to a gas. And I think one of the things that I know is that happens, that should be something that is consistent some way or another. And I think what they're showing us here is, okay, so it says the vapor pressure of sulfur dioxide is measured over a range of temperatures. Okay, so as the temperature increases, right, goes from 220 to 230 to 240 to 250, the vapor pressure increases. Oh, what does that mean? I think that means the hotter it gets, the more it's trying to escape from being a liquid. So that's promising. So at least conceptually, I think I understand that for sulfur dioxide, for things that are want to tend to go from being liquids to being gases, as I increase the temperature, the vapor pressure, its desire to form a gas, goes up. How does that sound?
So far,
Okay.
conceptually, sounds good.
Okay, so now there's this equation, the Clausius-Clapeyron equation, which I have to say I have not thought about in 15 or 20 years. So if you're taking this course in the fall of 2020, you could be in trouble. If you're taking it in the spring of 21 or 22, after I've done it a couple of times, maybe I'll be a little better at this. All right, so let's see if we can find the Clausius-Clapeyron equation. I think
It was up above, I think.
Is it?
Yeah.
All right. Yeah. It's all right. So what in the world? Let's go up here even further. Okay. So it says y is equal mx plus b, right? Yeah. So this is a straight line equation. So we got to understand. Oh my God, there's a lot going on here. All right. So apparently the natural log of the pressure, that's the y-axis. Okay. The natural log of the pressure is equal to the slope. Oh, okay, so here's the slope. It's a straight line, and it's just going to be a straight line equation, so that's why we get a straight value. Multiplied by x, which is the inverse of the temperature, plus some constant to move us away, that moves us away from the origin. Okay, so what we're really trying to do, so this equation apparently should give us a straight line, and the slope of that straight line is the enthalpy of vaporization. So looking at this graph, so at least now I can begin to recognize that the natural log of this pressure, the y-axis, the x-axis, the inverse of the temperature, and so the slope of this graph apparently is really related to the enthalpy of vaporization. So that's promising. So I think I'm beginning to understand what this graph is showing me, that it's plotted these two values, and the straight line slope is going to help us figure out what the enthalpy, how much energy does it take to vaporize, in this case, sulfur dioxide. All right. So, but in answer to your question, so how do I approach the reading of a graph? That part I think was consistent, because I was trying to read this graph, not really quite understanding what's going on with it, having not thought about it for a while. And so what did I do? I went and I looked at the axes and tried to understand what those axes were telling us. And I tried to look at the shape of the graph to try to make some sense of that. And in this case, I was able to at least relate it back to the form of a straight line equation and understand that one of the axes was the natural logarithm of the pressure, one of the axes was the inverse of the temperature, and so then the straight line is the slope that comes out of this. So I think in answer to your question, that was how I approached it. Okay, how about this one? So it's a picture, right? So again, on this one, this is called Explore Orbital Energies, right? Or it's going to ask us some information about or energy level diagrams. And what am I trying to figure out? Well, I'm going to look at, I start by looking at this axis over here. And it says, looks like energy is increasing over here on the left. And then across the graph, this looks to me sodium, magnesium. Okay, so this is period number 3 of the periodic table, right? And it's across the bottom, it is showing me information that I can try to figure out what it must mean. So this is the periods going across the periodic table, increasing energy. On this one, I approve of, and hopefully maybe by the time our students are looking at this, they will approve of it as well. I love the way that sodium, magnesium, aluminum, and silicon are getting lower across this graph, right? Because we've seen with the photoelectron spectroscopy data that the 1s electrons of these elements, chlorine and argon, are closer to the nucleus than they are for these elements. So this is actually also showing us a little bit of atomic radii, right? And the atomic radius, or the size, the volumetric size of the atoms. So start by looking at the axes, trying to understand what those things might be, and then I guess then you move into the body of the graph, which is to say, okay, look in here. Here, apparently, for all of these elements have the same electrons that look very similar in the 1s. They look very similar in the 2s, 3s, or the 2p, and then by the time then there's the 3s is a little bit different as we're starting off, and then the 3s orbital is filled for magnesium across to argon, and then that next electron goes into the 3p as they're going across. So what's the general rule? I think the general rule of thumb is look at the axes. I always apparently start on the left axis, the vertical axis, and then look at the horizontal axes and try to understand that, and then move into the body of the graph and try to make some sense of what's going on there.
Yeah, I think that was great. Do you have anything else to add in there, Dr. Hunter?
Oh no, I think I'm glad we found one that was hard for me, and I'm glad we found one that I'm much more comfortable with, and it's also one that relates much more to what our students are going to be encountering frequently.
Yeah, certainly. All right. I think that's all then.
Okay, all right. Thank you, Kevin.
Thank you, Dr. Hunter.